Imagine being born in prison. You never committed a crime. You never had a choice. You'll live your entire life in a 5-kilometer metal tube hurtling through absolute nothing. This is the generation ship, and we're seriously planning to build one. How many do you think will survive the journey? If you want to stay updated on these mind-blowing realities, please hit that subscribe button and give this video a like. Now let's get started. Let's be optimistic and say we build a ship that can cruise at 10% light speed. That's still a 43-year journey to our nearest neighbor. But Alpha Centauri might not have the kind of planet we need. The closest confirmed Earth-like exoplanet in the habitable zone is Proxima Centauri b, orbiting the red dwarf star Proxima Centauri, also about 4.2 light-years away. But other promising candidates, like some of the TRAPPIST-1 planets, are about 40 light-years distant. At 10% light speed, that's a 400-year voyage. At a more realistic 1% light speed, which is closer to what we could actually achieve with current or near-future technology, you're looking at 4,000 years. 4,000 years. Think about that. 4,000 years ago, humans were just beginning to develop writing. The pyramids of Giza hadn't been built yet. The entire span of recorded human history could fit into a single generation ship voyage and still leave room for another journey of equal length. This brings us to the heart of the generation ship concept. Since we can't travel fast enough to get anywhere in a single human lifetime, we have to bring multiple generations along for the ride. The ship becomes a tiny, self-contained world. Everything you need to survive, from air and water to food and medicine, has to be produced on board. There's no resupply mission. There's no turning back. You launch with maybe 500 to 1,000 people, and those people have children. Who have children? Who have children? Continuing for dozens or even hundreds of generations, until finally their descendants arrive at a new world that the original crew will never see. It sounds like science fiction because, well, it is. Writers have explored this idea for more than a century. Robert Goddard, one of the pioneers of rocketry, described the concept in 1918 in an essay called The Last Migration. Since then, countless novels and films have romanticized the journey, but when you dig into the actual science, when you look at what researchers like Frédéric Marin at the University of Strasbourg have calculated using sophisticated computer simulations, the romance evaporates pretty quickly. Let's talk about what happens to a closed population over time. This isn't speculation. We have data from isolated human populations on Earth, from conservation biology, and from detailed genetic modeling. When you take a small group of people and isolate them, several things start happening immediately, and none of them are good. First, there's genetic drift. In large populations, random changes in gene frequency tend to balance out. But in small populations, random events can have huge impacts. Maybe a person carrying a rare but beneficial gene dies in an accident before having children. That gene is gone forever. Maybe someone with a harmful recessive gene just happens to have lots of kids. Suddenly, that harmful gene becomes more common. Over time, genetic diversity decreases. The population becomes more genetically uniform. And that uniformity makes the entire group vulnerable. Think of it like this. Genetic diversity is your species' insurance policy against the unexpected. Different people have different immune responses, different tolerances to environmental factors, different susceptibilities to disease. When a new pathogen emerges in a diverse population, chances are good that at least some people will have natural resistance. Their genes will allow them to survive, reproduce, and pass on that resistance. But in a genetically uniform population, a single disease can sweep through like wildfire, sparing no one. Dr. Marin and his colleagues ran simulations using a program called Heritage, which models human populations on generation ships down to the genetic level. They gave each simulated person a full complement of 46 chromosomes, tracking thousands of genetic markers through hundreds of generations. What they found was sobering. Even starting with a population of 500 people, which is on the larger end of proposed crew sizes, genetic diversity plummeted over the course of a multi-century voyage. The simulations included something called the founder effect. This is a well-known phenomenon in population genetics. When you start with a small group, that group carries only a fraction of the genetic diversity present in the larger population they came from. Imagine scooping a cup of water from the ocean. That cup contains water, sure, but it doesn't contain a representative sample of every fish, every microorganism, every bit of diversity in the sea. The same thing happens with your founding crew. No matter how carefully you select them, they're just a cup of water from the ocean of human genetic diversity. And it gets worse. Space is not a friendly environment. Cosmic rays, high-energy particles that stream through the galaxy, constantly bombard everything in their path. Here on Earth, we're protected by our planet's magnetic field and thick atmosphere. These shields absorb or deflect the vast majority of cosmic radiation. But in deep space, there's no such protection. A generation ship would need massive shielding to protect its crew. We're talking meters of water, polyethylene, or other materials wrapped around the habitable sections of the vessel. And even then, some radiation gets through. Every time a cosmic ray strikes a cell in your body, there's a chance it will damage your DNA. Most of the time, your cells can repair the damage. Sometimes they can't, and the cell dies or becomes cancerous. But sometimes, the damage occurs in a sperm or egg cell, creating a mutation that gets passed on to the next generation. These are called germline mutations. In small doses, they're part of natural evolution. In the elevated radiation environment of deep space, they become a serious threat. Marin's team modeled this too. They calculated the expected rate of cosmic ray-induced mutations based on realistic shielding scenarios. What they discovered was that even with heavy shielding, the mutation rate aboard a generation ship would be significantly higher than on Earth. Some of these mutations would be neutral, having no real effect. Some would be harmful, reducing fertility, shortening lifespan, or causing genetic diseases. Very few would be beneficial. Here's where it connects to something I discussed in another video. If you haven't seen my breakdown of why interstellar travel might be a one-way trip, you should definitely check it out after this. It dives deeper into the physics and engineering challenges that make these journeys so unforgiving. The video is on the card above and pinned on the comments now. Combine genetic drift with elevated mutation rates, and you have a recipe for genetic degradation. Harmful mutations accumulate faster than natural selection can weed them out, especially in a small population where selection pressure is weak. Over generations, the crew becomes less healthy, less fertile, and more prone to genetic disorders. Infant mortality rises, lifespans shorten, the population starts to decline. But wait, you might say, can't we just start with more people? If 500 isn't enough, what about 1,000, 2,000? Here's the problem. The bigger your crew, the bigger your ship needs to be. And the bigger your ship, the more massive it becomes. Mass is the enemy of space travel. Every additional kilogram requires more fuel to accelerate, more structure to support, more resources to maintain. The engineering challenges grow exponentially. Current estimates suggest that a realistic generation ship, one that could sustain 500 people for several centuries, would need to mass somewhere in the range of tens of millions of tons. We're talking about a structure kilometers long, with agricultural decks, living quarters, industrial facilities, water treatment, power generation, and all the redundancies needed to keep everything running for longer than human civilization has existed. Building something like that would require resources on a scale we've never attempted. Launching it would demand propulsion systems we haven't invented yet. And even if we solve the engineering problem, even if we build this colossal ark and send it on its way, we're still facing the biological time bomb ticking inside every cell of every crew member. Let's talk about something called inbreeding depression. You've probably heard the term before, maybe in the context of endangered species or isolated island populations. It's what happens when relatives reproduce with each other over multiple generations. Now, before you think this is just about first cousins having children, understand that in a closed population of a few hundred people, everyone becomes related surprisingly fast. Do the math. You start with 500 unrelated individuals. They pair up and have children. That's generation 1. Those children grow up and have children of their own. That's generation 2. By generation 3 or 4, which is only about 80 to 100 years into the voyage, you've got a population where everyone shares common great-grandparents. By generation 10, the entire population is more closely related than typical third or fourth cousins, and the journey is barely getting started. When closely related individuals reproduce, there's an increased chance that harmful recessive genes will pair up. We all carry some recessive genetic mutations. In most cases, they don't matter because we inherit a healthy copy of the gene from our other parent. But when both parents carry the same recessive mutation, their children have a 25% chance of inheriting 2 copies, which means this mutation expresses itself. This is how genetic diseases like cystic fibrosis, sickle cell anemia, and Tay-Sachs disease work. In large, diverse populations, the odds of 2 carriers meeting and reproducing are relatively low, but in a small, closed population on a generation ship, those odds skyrocket. Over time, you'd see an increase in genetic disorders, birth defects, reduced fertility, and lower survival rates. The population's health deteriorates generation by generation. Scientists have studied this extensively in conservation biology. There's a concept called the minimum viable population, or MVP. This is the smallest number of individuals needed to ensure a population can survive long-term without suffering from inbreeding depression and genetic drift. For most mammal species, that number is somewhere between 500 and 1,000 individuals, assuming random mating and no external pressures. But here's the catch. That's for populations in stable environments with normal mutation rates and normal selective pressures. A generation ship is anything but stable. You've got elevated radiation, increasing mutation rates. You've got a completely artificial environment where natural selection might work differently than it does on Earth. You've got social and cultural factors that could affect who reproduces with whom. All of these factors push the minimum viable population higher. Some estimates suggest you'd need several thousand people to ensure long-term genetic health on a multi-century voyage. And as we already discussed, a ship that large becomes almost impossible to build and launch. But let's say we're optimistic. Let's say we carefully manage reproduction, maybe using genetic screening and sperm and egg banks from Earth to introduce new genetic diversity. We're essentially trying to engineer our way around evolution, and that brings up a whole new set of problems. Who decides who gets to reproduce? In a free society, people choose their partners based on love, attraction, compatibility. But on a generation ship, where genetic diversity is a matter of survival, you might need to impose reproductive controls. You might need to tell people they can't have children with their chosen partner because it would increase the risk of genetic disorders. You might need to require people to use donor genetic material instead of conceiving naturally. Think about the psychological and social implications. You're asking people who were born on the ship, who had no choice in the mission, to sacrifice their reproductive freedom for the good of a mission they never signed up for. You're creating a society where individual desires are subordinated to collective genetic management. That's a recipe for resentment, rebellion, and social breakdown. And social breakdown is perhaps the most underestimated threat to generation ships. We've spent a lot of time talking about genetics and radiation, but the human element might be the most unpredictable variable of all. Imagine living your entire life in a metal cylinder a few kilometers long. You never see an open sky. You never feel rain on your face. You never walk through a forest or swim in an ocean. The only nature you know is the carefully managed agricultural decks where food is grown. Every breath you take has been recycled thousands of times. Every drop of water you drink has passed through the bodies of your ancestors. You're surrounded by the same few hundred faces, the same corridors, the same routines, day after day, year after year, decade after decade. Now imagine knowing that you will die on this ship. Your children will die on this ship. Your grandchildren will die on this ship. Maybe, if you're part of generation 15 or 20, your great-great-great-grandchildren will reach the destination. But you're born in transit, you live in transit, and you die in transit. Your entire existence is a bridge between departure and arrival, never experiencing either. How do you maintain morale under those conditions? How do you give people a sense of purpose? The original crew, the ones who volunteered for the mission, they have their motivation. They're pioneers, heroes, the people who took the first step toward making humanity a multi-star species. But what about Generation 5? Generation 10? They didn't volunteer. They were born into this. They might start to question the mission. Why are we doing this? What's the point? Who decided that reaching some distant planet was worth condemning hundreds of generations to life in a tin can? There's a concept in psychology called the third generation problem. It's been observed in immigrant families, in isolated communities, in any group where the founding generation has a strong purpose and identity. The first generation knows why they're there. They made the choice. The second generation grows up hearing stories, understanding the sacrifice, feeling connected to the mission. But the third generation, they're further removed. The mission is just the way things are, not something they chose or even something they feel particularly connected to. By the fourth, fifth, or sixth generation, that sense of purpose can erode completely. On Earth, when a community loses its sense of purpose, people can leave. They can migrate, find new communities, create new identities. But on a generation ship, there's nowhere to go. You're stuck. And that kind of existential claustrophobia could lead to psychological breakdown on a mass scale. Depression, anxiety, violence, suicide. These could become epidemics, further reducing the population and threatening the mission. There have been some proposed solutions. One idea is to maintain a strong cultural narrative, almost a religion, centered around the mission. You indoctrinate each generation from birth with the importance of reaching the destination, the nobility of the sacrifice, the honor of being part of this great journey. You create rituals, celebrations, and social structures that reinforce this narrative constantly. In other words, you turn the mission into the foundation of your entire society's identity. But here's the dark side of that approach. You're essentially creating a cult. You're using social control and psychological manipulation to keep people compliant. And what happens when someone questions the narrative? What happens when a group decides they don't believe in the mission anymore and wants to turn the ship around or change course? You're looking at potential civil conflict, possibly even civil war, on a closed vessel where any major conflict could be catastrophic. And let's talk about leadership and governance. Who's in charge of a generation ship? The original crew might set up a government, a set of laws, a chain of command. But what happens over generations? Does power pass democratically? Does it become hereditary? What if a corrupt or incompetent leader takes control? On Earth, bad governments can be overthrown, and people can flee to other countries. On a generation ship, you're stuck with whatever system evolves, and history shows us that power tends to concentrate and corrupt over time, especially in closed systems. There's also the knowledge problem. A generation ship needs to maintain extremely sophisticated technology for centuries. That means each generation needs to understand engineering, biology, computer science, physics, medicine, agriculture, and dozens of other fields. You need to preserve not just the knowledge itself, but the ability to teach it, to apply it, to innovate when things go wrong. Because things will go wrong. A critical system will fail, a disease will emerge, a meteor will strike the ship. Whatever can go wrong over a span of centuries probably will, and when it does, you need people who understand the systems well enough to fix them. But how do you ensure that knowledge passes intact from generation to generation? Books can be lost or damaged. Digital storage can corrupt. Teachers can make mistakes or deliberately withhold information. Over hundreds of years, knowledge can degrade like a game of telephone, with each generation understanding a little bit less than the last. There's a historical example that illustrates this perfectly. In the Pacific, there were Polynesian cultures that maintained sophisticated navigation techniques, using stars, ocean swells, and bird behavior to cross thousands of kilometers of open ocean. This knowledge was passed down orally from master navigators to apprentices. But in some island communities, after contact with Europeans and the introduction of written charts and compasses, the traditional knowledge began to fade. Within just a few generations, some communities lost the ability to navigate using traditional methods. Now imagine that happening on a generation ship, but with critical life support systems instead of navigation. One generation fails to properly train the next, and suddenly nobody knows how to fix the water recyclers when they break down. Some researchers have suggested carrying extensive digital libraries, artificial intelligence systems, and automated repair mechanisms to preserve knowledge and maintain systems. But that introduces another layer of dependency and risk. What if the AI malfunctions? What if a computer virus corrupts the library? What if the crew becomes so dependent on automated systems that they lose the ability to think critically and solve problems independently? You could end up with a population that's essentially cargo being carried by machines they no longer understand, praying those machines don't fail. Now let's address one of the most fundamental biological challenges: closed-loop life support. Every generation ship design requires a completely self-sustaining ecosystem. You need to recycle air, water, and waste with near-perfect efficiency. Any loss, any inefficiency compounds over time. Lose 1% of your water per year, and in a century, you've lost more than half your supply. There's no rain to replenish it. There's no lake to draw from. What you launch with, minus whatever you can extract from asteroids or comets along the way, is what you have. Current life support technology, like what we use on the International Space Station, isn't even close to what a generation ship would need. The ISS relies on regular resupply missions from Earth. Water is partially recycled, but not completely. Air is refreshed with tanks of oxygen brought up on cargo ships. Food is almost entirely supplied from Earth. The station has been continuously inhabited since the year 2000, but it's never had to be truly self-sufficient. The most advanced closed-loop experiment we've attempted was Biosphere 2, built in the Arizona desert in the late 1980s. The idea was to create a sealed environment with multiple ecosystems, including a rainforest, ocean, desert, and agricultural areas where a small crew could live completely cut off from the outside world. The first mission began in 1991 with 8 people sealed inside for 2 years. It was a disaster. Oxygen levels dropped so low that they had to pump in air from outside, breaking the closure. Carbon dioxide levels fluctuated wildly. Most of the vertebrate species went extinct. 19 of 25 small vertebrate species died out. Certain insect populations exploded, including cockroaches and ants. Morning glory vines overgrew other plants. Soil microbes produced unexpected amounts of carbon dioxide and consumed oxygen. The crew suffered from hunger, low morale, and internal conflicts. And that was in a facility on Earth, where help was available if things went catastrophically wrong, where the environment outside was already life-supporting. Now imagine that same experiment, but in the vacuum of space for 400 years with no possibility of outside assistance. The challenges multiply astronomically. Plants are supposed to be the foundation of a generation ship's life support. Through photosynthesis, they consume carbon dioxide and produce oxygen. They provide food. They process some waste products. But managing a stable agricultural ecosystem in an artificial environment is incredibly complex. You need the right balance of plant species, soil microbes, pollinators, temperature, humidity, light, and nutrients. Tip that balance in any direction, and the whole system can collapse. On Earth, ecosystems are stabilized by their sheer scale and diversity. If one species has a bad year, others compensate. Nutrients cycle through vast reservoirs in soil, oceans, and atmosphere. But on a generation ship, everything is miniaturized and simplified. You might have a few dozen crop species instead of the hundreds of thousands of plant species on Earth. Your soil volume is measured in tons, not gigatons. Your atmosphere is contained in chambers, not wrapped around a planet. That system is inherently fragile. And then there's the food itself. Humans need a diverse diet to stay healthy. We need proteins, fats, carbohydrates, vitamins, minerals, and trace elements. You can't just grow wheat and potatoes and call it done. You need variety. That means multiple crop species, each with different growing requirements. You probably need some form of protein, whether that's fish in aquaculture tanks, insects, or vat-grown meat. Each addition makes the ecosystem more complex and harder to manage. Let's talk about waste. Every person produces waste. Solid waste, liquid waste, exhaled carbon dioxide, heat. In a closed system, there's no way to throw things. Everything must be recycled. Human waste has to be processed to reclaim water and nutrients. Organic matter has to be composted or broken down to enrich soil. Inorganic waste has to be sorted, stored, or somehow repurposed. Nothing can be wasted because you're not getting any more resources. But recycling is never 100% efficient. There's always some loss. Water molecules break down and escape as hydrogen and oxygen. Nutrients get locked up in forms that plants can't use. Materials degrade and can't be fully recovered. Over decades and centuries, these tiny losses add up. Your ship is slowly bleeding resources, and there's no way to replace them unless you stop at asteroids or comets to mine ice and minerals. But stopping means delaying the mission, extending the number of generations needed, which increases all the other risks we've discussed. Some designs propose capturing resources from the interstellar medium itself, the incredibly thin gas that exists between stars. But we're talking about densities of maybe 1 atom per cubic centimeter. To gather meaningful amounts of material, you'd need to sweep through enormous volumes of space using massive electromagnetic scoops or other collection systems. The engineering for that is purely theoretical right now. We've never built anything even remotely like it. And there's another issue: energy. A generation ship needs power, lots of it. Power for lights, for agriculture, for life support, for computers, for propulsion, for everything. Where does that energy come from? Solar panels work great near a star, but once you're deep in interstellar space, the sun is just another dim point of light. Solar energy drops off with the square of the distance. By the time you're even halfway to the nearest star, solar panels are essentially useless, so you need another power source. The most commonly proposed solution is nuclear fusion. If we can develop working fusion reactors, They could theoretically run for decades on relatively small amounts of fuel, like deuterium and helium-3, but fusion power is still experimental. We've been working on it for more than 70 years, and we still don't have a working fusion power plant on Earth. The ITER project, the largest fusion experiment ever attempted, might achieve net energy gains sometime in the 2030s or 2040s. Even then, that's a massive experimental reactor, not something you could miniaturize and make reliable enough for a centuries-long space voyage. Fission reactors are proven technology, but they produce radioactive waste and require fuel that's heavy and limited. You'd need to carry enough uranium or plutonium to last the entire journey, or develop breeder reactors that produce more fuel than they consume. Either way, you're dealing with significant mass and radiation shielding requirements on top of everything else. Let's assume we solve the power problem. You've got fusion reactors humming away, providing all the energy you need. You've got a closed-loop life support system that's miraculously stable. You've managed the genetic problems through careful population management. You've maintained social cohesion across dozens of generations. You're actually going to make it. But then comes perhaps the most underestimated challenge of all. Arriving a generation ship isn't like a car you can just slow down by hitting the brakes. In space, there's no friction. Whatever speed you've accelerated to, you're going to maintain unless you actively decelerate. And deceleration requires just as much energy as acceleration. If you spent decades accelerating to 10% the speed of light, you need to spend decades decelerating, burning fuel the entire time. This is known as the tyranny of the rocket equation. The amount of fuel you need grows exponentially with the change in velocity you're trying to achieve. To accelerate a massive ship to a significant fraction of light speed and then decelerate again at the destination, you need fuel, lots of fuel, so much fuel that the fuel itself becomes most of the ship's mass, and the more massive the ship, the more fuel you need, which makes it even more massive, which requires even more fuel. It's a vicious cycle. Some proposed designs try to get around this with clever tricks. One idea is the Bussard ramjet, a theoretical spacecraft that uses magnetic fields to scoop up hydrogen from the interstellar medium and use it as fusion fuel. In theory, you'd never run out of fuel because you'd be collecting it as you go. You'd accelerate continuously for the first half of the journey, then flip around and decelerate for the second half, using the same fuel collection system. It's elegant on paper, but the reality is far messier. The interstellar medium is extraordinarily thin. You'd need a magnetic scoop hundreds or even thousands of kilometers wide to collect enough hydrogen to matter. The energy required to generate and maintain those magnetic fields might be more than you'd gain from the fusion process. And there's drag. Yes, even in the near vacuum of space, when you're moving at a significant fraction of light speed and trying to scoop up particles, you create resistance. That drag could actually slow you down more than the fusion fuel speeds you up. Most physicists who've analyzed the Bussard ramjet concept in detail have concluded it probably wouldn't work, at least not with any technology we can currently envision. Another approach is the laser sail. Instead of carrying fuel, you build an enormous, ultra-light reflective sail attached to your ship. Back in the solar system, you construct a massive array of lasers, perhaps powered by solar energy. These lasers focus their beams on your sail, pushing the ship with photon pressure. Because the energy source stays behind, you don't have to carry fuel for acceleration. You can reach very high speeds, potentially up to 20 or 30% the speed of light. The Breakthrough Starshot initiative, funded by tech billionaires and advised by scientists like the late Stephen Hawking, is exploring this concept for tiny probe missions. They're talking about sending gram-scale spacecraft with meter-wide sails to Alpha Centauri. accelerated by ground-based lasers to 20% light speed. If it works, these probes could make the journey in about 20 years. But there's a big difference between a gram-scale probe and a multi-million-ton generation ship. For a generation ship, the sail would need to be enormous, possibly hundreds of kilometers across. The lasers would need to be phenomenally powerful and precisely aimed across distances of trillions of kilometers. And here's the killer: a laser sail only helps you accelerate. Once you turn off the lasers or get too far away for them to be effective, you're coasting. You have no way to slow down at the destination unless you somehow build another laser array at the target star system and aim it back at you. But there's nobody there to build it. You're on your own. Some designs propose using the sail as a magnetic parachute, interacting with the target star's stellar wind to slow down. Others suggest detaching part of the sail and using it as a reflector, bouncing the laser light back onto the main sail to create a braking force. These ideas are theoretically possible but phenomenally difficult to execute. You're talking about precision maneuvers with a structure the size of a small country, performed across interstellar distances after centuries of travel, during which anything could have degraded or malfunctioned. And let's talk about navigation. Space is big, but it's not empty. There are rogue planets, asteroids, comets, dust clouds, and all sorts of debris floating around. At low speeds, hitting a pebble-sized rock is annoying. At 10% the speed of light, hitting that same pebble releases energy equivalent to a nuclear bomb. The kinetic energy of an object is 1/2 its mass times its velocity squared. When velocity is a significant fraction of the speed of light, even tiny masses carry devastating energy. Imagine your generation ship plowing through space at 30,000 kilometers per second. A grain of sand, something with a mass of perhaps 1 milligram, hits your hull. The kinetic energy released is roughly equivalent to a hand grenade exploding. A pebble weighing 1 gram, that's like several tons of TNT. A rock the size of your fist could vaporize entire sections of the ship. This means you need shielding, and not just against radiation. You need physical armor or some kind of active defense system. One proposed solution is to put a sacrificial shield ahead of the ship, essentially a thick slab of material, maybe ice or metal, positioned kilometers in front of the main vessel. Incoming particles hit the shield, vaporize, and the expanding plasma disperses before reaching the ship proper. But maintaining and replacing that shield over centuries of travel is another engineering nightmare. You also need sensors looking ahead constantly, tracking any objects in your path. If you detect something big enough to be a threat, you need to maneuver around it. But maneuvering a multi-million-ton ship isn't like steering a car. Any course change requires thrust, which requires fuel or energy, which is limited. Too many course corrections and you might not have enough fuel left to decelerate at the destination. It's a constant balancing act between safety and mission parameters. Then there's time dilation, a consequence of Einstein's special relativity. When you're moving at a significant fraction of light speed, time literally passes differently for you than for people at rest. At 10% light speed, the effect is small, only about 0.5%, but at higher speeds it becomes dramatic. If you could somehow reach 90% light speed, time for you would pass about twice as slowly as time for people back on Earth. A journey that takes 40 years by your clock would be nearly 90 years back home. This creates strange paradoxes for a generation ship. The people on board experience less time than the rest of the universe. But relativity doesn't help you much at the speeds we're talking about for realistic generation ships. At 1 to 10% light speed, time dilation is negligible. You're still looking at centuries of subjective time for the crew. It's only if you could reach much higher speeds, 70, 80, 90% of light speed, that time dilation becomes a significant factor. and reaching those speeds with a massive ship is almost certainly impossible with any foreseeable technology. Let's circle back to the human factor, because even if you solve all the engineering problems, you still have to deal with the psychological and social realities of multi-generational confinement. Researchers have started studying this seriously in recent years, recognizing that the human element might be the weakest link in the entire chain. Cameron Smith, an anthropologist at Portland State University, has written extensively about the cultural dynamics of multi-generational space voyages. He points out that human cultures are never static. They evolve, sometimes rapidly. Language changes, beliefs shift, social norms transform. On Earth, cultures evolve through interaction, migration, trade, and conflict with other cultures. But a generation ship is isolated. It has no external cultural inputs. How does culture evolve in that context? One possibility is stagnation. Without external pressures or new ideas, the culture becomes rigid and unchanging. Tradition becomes everything, because tradition is all they have. This could help maintain social cohesion and preserve knowledge, but it could also lead to a brittle society that can't adapt to unexpected challenges. If something comes up that the traditional knowledge doesn't address, the culture might lack the flexibility to respond effectively. Another possibility is fragmentation. Over generations, different groups within the ship develop different subcultures. Maybe one group focuses on agriculture, another on engineering, another on governance. These groups develop distinct identities, values, and even dialects. If those differences harden into factions, you could see the ship's population split into competing tribes. In the worst case, that competition turns violent, leading to civil war in a confined space where any major conflict could doom everyone. There's also the issue of mental illness. Rates of depression, anxiety, and other psychological disorders might be higher in the artificial confined environment of a generation ship. How do you provide mental health care across generations? Do you have trained psychologists and psychiatrists? How do you maintain that knowledge and practice? What if mental illness becomes stigmatized in the ship's culture, leading people to hide their symptoms rather than seek help? Untreated mental illness could lead to violence, suicide, or sabotage, any of which could be catastrophic in a closed system. And what about crime? Every human society has had to deal with people who break rules, who harm others, who steal or destroy property. On Earth, we have justice systems, prisons, rehabilitation programs. What does justice look like on a generation ship? You can't really imprison someone long-term because every person is a valuable part of the population and ecosystem. You need their labor. You need their genetic contribution. But you also can't let dangerous individuals roam free. Do you use exile, confining criminals to isolate sections of the ship? Do you use corporal punishment? Do you resort to execution for serious crimes, even though that reduces your already fragile population? These are questions with no easy answers. Then there's the question of what happens when you finally arrive. After centuries of travel, after dozens of generations born and died in transit, the ship reaches its destination. You're in orbit around a new world, a planet that might be habitable. But might be is doing a lot of work in that sentence. Before you left Earth, you identified this planet as potentially habitable based on observations from telescopes. You detected oxygen in its atmosphere, water vapor, a size and mass similar to Earth's, a distance from its star that puts it in the habitable zone where liquid water can exist. All good signs. But those observations were made from light years away. You were looking at light that left that planet decades or centuries ago. You couldn't see fine details. You couldn't detect microorganisms or toxins in the soil. You couldn't map weather patterns or tectonic activity. You were making an educated guess based on limited data. Now you're here and you get your first close-up look. Maybe the planet is perfect, a pristine world with breathable air, drinkable water, edible plants, and no dangerous predators or diseases. That would be extraordinarily lucky, almost miraculous. More likely, there are problems. Maybe the atmosphere has oxygen, but it also has high concentrations of methane or sulfur compounds that are toxic to humans. Maybe the water is there, but it's laden with heavy metals or alien microorganisms. Maybe the temperature swings are more extreme than you expected. Maybe the gravity is 15 or 20% higher than Earth's, which doesn't sound like much, but would be exhausting over a lifetime and could cause serious health problems. Maybe there are plants, but they use different biochemistry, and you can't digest them. Maybe there are native microbes that see your biology as a resource and attack your cells. You've just spent 400 years traveling to this place. Thousands of people have lived and died to get you here. And now you discover the planet isn't quite what you hoped. What do? You can't go back. You don't have the fuel or resources for another multi-century journey. You're stuck, so you adapt. You live in sealed habitats on the surface, not much different from the generation ship you just left, except now you have a planet's gravity and resources to work with. You slowly, carefully, attempt to terraform the planet, altering its atmosphere and ecosystem to make it more Earth-like. But terraforming is a process that takes centuries or millennia, if it's even possible. You're looking at dozens more generations living in artificial environments before anyone can step outside without a suit. Or maybe you take a more aggressive approach. Maybe you release genetically engineered organisms designed to alter the planet's chemistry. Maybe you seed the oceans with Earth algae to change the atmospheric composition. But ecosystems are complex and unpredictable. Introduce one species, and it might interact with native life in ways you didn't anticipate. You could trigger a cascade of extinctions, destroy the very biosphere you were hoping to use, or create a hybrid ecosystem that's hostile to both native and Earth life. And if there is native life, even microbial life, you face an ethical question that humanity has never had to seriously answer. Do we have the right to alter or destroy an alien biosphere to suit our needs? From a survival standpoint, the answer might be yes. You traveled all this way, you need a place to live, and this is the only option. But from an ethical standpoint, you're potentially committing genocide against an entire world's worth of unique life forms that evolved independently of Earth. You're wiping out billions of years of evolutionary history because it's inconvenient for you. Some scientists and philosophers argue that if we ever find even microbial alien life, we should leave it alone, treat it as a nature preserve, and find somewhere else to colonize. But if you're on a generation ship and you've just arrived at the one planet you targeted, you don't have a somewhere else. You're there, and you have to make a choice in real time with the survival of your people hanging in the balance. Let's assume the planet is habitable, or at least workable. You establish a colony. But here's something people don't often think about. The generation ship crew and the colonists might have become two different populations with different needs and perspectives. The ship has been home for generations. There are people who were born there, who've lived their entire lives there, who might not want to leave. The ship is familiar, it's controlled, it's known. The planet, even a habitable one, is alien, unpredictable, and dangerous. You could see a split. Some people stay on the ship, preferring the environment they know. Others go to the surface to build the colony. Over time, these two groups diverge genetically and culturally. The ship people adapt to low gravity, recycled air, and artificial environments. The planet people adapt to the new world's gravity, atmosphere, and ecosystem. A few generations later, they're almost like different species, and if resources are limited, they might come into conflict. The ship people need supplies from the planet. The planet people see the ship as a drain on resources. You've crossed light years to escape Earth's problems, and you've recreated them in a new star system. There's another scenario that's even darker. What if, during the centuries of travel, technology back on Earth advances rapidly? Remember, you left with the best technology available at the time of departure. But back on Earth, science and engineering keep progressing. Maybe 50 years after you left, someone invents a faster propulsion system. A new ship launches, traveling at 30% light speed instead of your 10%. They leave decades after you, but arrive decades before you. When you finally reach your destination after 400 years of struggle, sacrifice, and suffering, you find the planet already colonized. There's a thriving human settlement that's been there for a century. They used better technology, took a faster route, and beat you there. Your entire journey, your entire multi-generational saga was pointless. You're not pioneers. You're just the people who took the slow boat. How do you cope with that psychologically? How does your society, which has defined itself entirely around being the first to reach a new world, handle the realization that you're not? Do you integrate with the existing colony, becoming second-class citizens in a world you thought would be yours? Do you move on, searching for another planet, even though you're exhausted and depleted? Do you turn the ship around and try to go back to Earth, knowing that by the time you arrive, everyone you knew will have been dead for 800 years? This is called the weight calculation, and it's a real problem in discussions of interstellar travel. If technology keeps improving, there's always an incentive to wait for better ships. But if everyone waits, nobody ever goes, and if you do go, you risk being overtaken by later, faster missions. It's a paradox with no clear solution. Some researchers have suggested that the first interstellar missions won't be generation ships at all. They'll be small, fast probes like breakthrough starshots, proposed laser sail missions, send thousands of tiny probes to nearby stars. They arrive in 20 or 30 years, relay data back, and give us detailed information about those systems. Then, if we find a truly habitable planet, we can decide whether to send humans. Maybe by then we'll have better technology, maybe even cryogenic sleep or some form of suspended animation that allows people to sleep through the journey rather than living through it. Cryogenic sleep is a staple of science fiction, and it would solve many of the problems we've discussed. No multi-generational social dynamics, no inbreeding, no psychological strain of living in confinement for centuries. You go to sleep near Earth, wake up near your destination. But the reality is we're nowhere close to that technology. We can freeze cells, embryos, even some small organisms, and revive them. But a whole human body, that's vastly more complex. When you freeze tissue, ice crystals form, and those crystals tear apart cell membranes. The damage is catastrophic. Cryoprotectants can reduce ice formation, but they're toxic at the concentrations needed to prevent freezing damage. There's a technique called vitrification where you cool tissue so fast that it solidifies into a glass-like state without forming crystals, but doing that uniformly throughout an entire human body and then reversing it without damage is far beyond our current capabilities. Some researchers are exploring induced torpor, a state similar to hibernation in bears or suspended animation in certain animals. If we could slow human metabolism drastically, people could sleep for months or even years at a time, aging much more slowly and requiring far fewer resources. But human biology doesn't naturally support this. We'd need to fundamentally alter human physiology, either through genetic engineering or through drugs and technology we haven't invented yet. And even if we could induce torpor, someone would need to stay awake to monitor the systems, which brings us back to a smaller scale version of the same problems. There's another approach that sounds like something out of a horror movie, but is seriously discussed in academic circles. Sending frozen embryos instead of living people. You'd load a ship with thousands of frozen human embryos, genetic material representing a diverse population. The ship would also carry artificial wombs, robotic caretakers, and educational AI systems. When the ship arrives at its destination, the robots thaw the embryos, gestate them in artificial wombs, and raise the children using programmed knowledge and skills. This solves the genetic diversity problem. You can carry embryos representing thousands of individuals, ensuring a healthy gene pool. It solves the resource problem during transit because embryos don't need food, water, or air. It solves the psychological problem of multi-generational confinement because nobody's actually alive during the journey. The first generation is born at the destination, but it creates a host of new problems. First, we don't have reliable artificial womb technology for humans. We've made progress with animal embryos, but gestating a human from conception to birth entirely outside a biological mother is still theoretical. Second, who raises these children? Robots programmed with educational software. That's an extraordinary amount of trust to place in AI systems. What if the AI malfunctions? What if its programming is inadequate for the psychological needs of developing children? What if the children grow up emotionally stunted, unable to form proper relationships, traumatized by being raised by machines? And there's the ethical dimension. You're creating human beings and condemning them to a life they had no choice in. They didn't volunteer for this mission. They were created specifically to colonize an alien world, born into a situation they can't escape. Is that fundamentally different from creating children on Earth who also don't choose to be born? Maybe, maybe not. But it feels different when you're deliberately engineering humans as colonization tools. Let's step back and look at the bigger picture. Why are we even talking about generation ships? The usual argument is species survival. The idea is that humanity is vulnerable as long as we're confined to one planet. An asteroid impact, a supervolcano, a nuclear war, a pandemic, a gamma-ray burst. Any number of catastrophes could wipe us out or set civilization back to the Stone Age. By spreading to other star systems, we ensure that even if Earth is destroyed, humanity continues somewhere else. It's a compelling argument, and there's truth to it. Keeping all our eggs in one planetary basket is risky, but generation ships might not be the solution. They're extraordinarily expensive, risky, and slow. Before we can build generation ships, we'd need to master living in space on a much smaller scale. We'd need permanent, self-sustaining colonies in orbit around Earth, on the Moon, on Mars, in the asteroid belt, on the moons of Jupiter and Saturn. If we can build a self-sustaining colony on Mars, that already gives us a backup for humanity. Mars has resources, water ice, minerals, carbon dioxide that can be converted to fuel and oxygen. It's much closer than the nearest star, only months away instead of centuries. If something happens to Earth, Mars could survive and eventually help rebuild. The same goes for orbital habitats or lunar colonies. And here's the thing. If we can't make a closed-loop ecosystem work on Mars or in the asteroid belt, we definitely can't make one work on a generation ship. Mars is a proving ground. If we try to build a self-sustaining colony there and it fails, people can be evacuated to Earth. The failure is disappointing but not fatal. If a generation ship fails halfway to another star system, everyone dies. There's no rescue, no evacuation, no second chance. So the realistic path to the stars probably goes through the solar system first. We build colonies on Mars, the Moon, in orbit, on Ceres, on the moons of Saturn. We learn how to create truly closed-loop life support. We learn how to maintain genetic diversity in small populations. We learn how to govern isolated communities. We develop fusion power or some other high-energy propulsion system. We send probes to nearby stars and get detailed data about planets there. Maybe in 200 years, maybe in 500 years, we're ready to attempt a generation ship. By then, the colonies throughout the solar system are thriving. The gene pool for the mission can be drawn from billions of people across dozens of worlds. The technology is proven over centuries of use. The cultural and psychological challenges have been studied and addressed. The first-generation ship isn't a desperate gamble. It's a calculated expansion of a spacefaring civilization that's already multiplanetary. Or maybe by then we've developed technology that makes generation ships obsolete. Maybe we have fusion drives that can accelerate ships to 50% light speed, cutting travel time to nearby stars to a decade or two. Maybe we've cracked cryogenic sleep or digital consciousness transfer. Maybe we've discovered physics beyond our current understanding that allows for faster-than-light travel, or wormholes, or some other method we can't even imagine yet. That's the other side of the weight calculation. Technology might advance enough to make the entire concept of generation ships unnecessary, but we don't know if or when that will happen. We can't base our plans on technologies that might never exist. So we plan with what we have and what we can reasonably extrapolate from current science. There's also a philosophical question lurking beneath all of this. Should we go to the stars at all? Is it humanity's destiny to spread throughout the galaxy, or is that just hubris? Some people argue that we should focus on fixing Earth's problems before we think about colonizing other worlds. We have poverty, inequality, climate change, biodiversity loss, political instability. Shouldn't we address those issues first? The counter-argument is that space exploration and solving Earth's problems aren't mutually exclusive. The amount of money spent on space programs is tiny compared to global GDP. NASA's budget is about 0.5% of the US federal budget. The European Space Agency, the Chinese space program, and all other space agencies combined represent a minuscule fraction of global economic activity. We could double or triple funding for space exploration, and it would barely dent budgets for healthcare, education, or environmental protection. Moreover, space exploration drives technological innovation that benefits life on Earth. Satellite technology enables global communications, weather forecasting, GPS navigation, and environmental monitoring. Research into closed-loop life support for space missions advances recycling and sustainability technologies on Earth. Studying other planets helps us understand our own climate better. The inspirational and educational value of space exploration is harder to quantify, but arguably just as important. But there's a deeper ethical question when it comes to interstellar colonization. If we do find habitable planets, and if those planets have native life, even just microbes, do we have the right to interfere? Carl Sagan, the famous astronomer and science communicator, argued that if we find a planet with any form of life, even primitive life, we should leave it alone. That planet belongs to its own biosphere, not to us. We should be observers and students, not conquerors. Others, like the late physicist Freeman Dyson, took a more pragmatic view. If a planet has only microbial life and we need it for survival, we should use it, but carefully and with as much respect for the native biosphere as possible. Maybe we can coexist with the native life, creating hybrid ecosystems. Maybe we can even enhance and accelerate the native evolution, acting as benevolent stewards rather than exploiters. And what if we find a planet with intelligent life? Not necessarily technological civilization, but intelligent animals, perhaps as smart as dolphins or great apes or even early humans. Do we avoid contact entirely? Do we observe from orbit? Do we attempt communication? The prime directive from Star Trek, the idea of non-interference with less advanced civilizations, is a noble philosophy in fiction. But in reality, if we've traveled centuries to reach a planet and it's our only option for survival, would we really turn away because there are intelligent beings already there? These are questions without clear answers. They're the kind of moral dilemmas that humanity has never had to face, because we've never been in a position to colonize another world with life on it. But if we're serious about interstellar travel, we need to think about these issues now, before we're faced with them in practice. We need to develop ethical frameworks, international or interplanetary agreements, guidelines for how we interact with any life we find. There's also the question of who decides to go and who gets to decide who goes. A generation ship mission would require enormous resources, probably more than any single nation could provide. It would need to be an international effort, or perhaps a coalition of the wealthiest nations or corporations. But whoever funds it gets to control it, and that means they get to decide who's on board. Do you select the crew based on genetic diversity, choosing people from all over the world to maximize the gene pool? That makes scientific sense, but it creates a ship full of people from vastly different cultures, languages, and backgrounds. How do they govern themselves? Whose laws and customs apply? What language do they speak? Or do you select from a single culture or nation, ensuring social cohesion and shared values? That might make the social dynamics easier in the short term, but it reduces genetic diversity and creates a colonial enterprise where one culture expands to the stars while others are left behind. It also raises the specter of space colonialism, where wealthy nations or corporations claim entire star systems as their territory. What about the selection criteria for individuals? Do you choose the smartest, healthiest, most skilled people? That creates an elite mission, the best of humanity heading to the stars. But it also means leaving behind people who might be perfectly capable but don't fit narrow criteria. And what about genetic diseases or disabilities? Do you exclude people with genetic conditions that might be passed on to future generations? That's eugenics, and humanity has a dark history with that concept. Or do you try to create a representative sample of humanity, including people with various backgrounds, abilities, and genetic profiles? That's more egalitarian, but it might not be optimal for survival. If you're trying to establish a viable population in one of the harshest environments imaginable, do you really want to compromise on health and capability in the name of inclusivity? These are uncomfortable questions, and they pit values against each other in ways that don't have easy resolutions. Survival versus ethics, diversity versus cohesion, meritocracy versus equality. Different people will answer these questions differently based on their values, their culture, their philosophy. And those differences could become sources of conflict both in selecting the crew and among the crew once the journey begins. Let's talk about the economics for a moment, because the cost of a generation ship would be staggering. Some estimates put it at trillions of dollars, possibly tens of trillions, depending on the size and technology. That's more than the GDP of most countries. It would require global cooperation on a scale humanity has never achieved. The International Space Station, one of the most expensive projects ever undertaken, cost about $150 billion over several decades and involved just 15 countries. A generation ship would be orders of magnitude more expensive. Where does that money come from? Government funding. That means convincing taxpayers across multiple nations to support a project that won't produce results for centuries, long after they and their grandchildren are dead. Private funding? That means corporations or billionaires control the mission, which raises questions about accountability and who benefits. Do they own the new colony? Do they get to make the laws there? Do they exploit resources from the destination star system for profit? There's also the opportunity cost. The money spent on a generation ship could fund countless projects on Earth: healthcare, education, infrastructure, renewable energy, climate change mitigation. Is it morally defensible to spend trillions on sending a few thousand people to another star when billions of people on Earth lack basic necessities? The counter-argument is, again, that this is a false choice. We can do both, but in practice, resources are finite, and money spent on one thing can't be spent on another. Governments and societies have to make choices about priorities. And in a democratic system, convincing people to prioritize a multi-century space mission over immediate needs is a hard sell. This might be why, if generation ships ever happen, they'll likely be funded by a combination of sources: government seed money, private investment, crowdfunding from millions of people who believe in the mission, resource extraction from asteroids and other bodies in the solar system that helps pay for the construction, and perhaps even lottery systems where people pay for a chance to be selected for the crew. But there's a darker possibility. Maybe generation ships only happen in a crisis scenario. Maybe climate change or nuclear war or some other catastrophe damages Earth so severely that a generation ship becomes a lifeboat, a desperate attempt to preserve humanity before it's too late. In that scenario, the mission wouldn't be about exploration or expansion. It would be about survival, and the urgency might override some of the ethical and economic concerns we've discussed. Imagine Earth in 200 years. Climate change has made large parts of the planet uninhabitable. Sea levels have risen, drowning coastal cities. Droughts and famines are common. Political instability and resource wars are constant. The global population has crashed from billions to maybe a billion or less. Civilization is teetering on the edge of collapse. In that desperate context, a coalition of survivors builds a generation ship. It's a Hail Mary, a last-ditch effort to ensure that humanity doesn't go extinct. The ship is smaller than the optimistic designs we've discussed, maybe only a few hundred people, because that's all they can support. Genetic diversity is compromised, but it's better than nothing. The technology is patched together from whatever's available, not the cutting-edge systems we'd ideally want. The destination is the nearest star with a potentially habitable planet, even if the data is uncertain, because beggars can't be choosers. The ship launches. It's a grim, desperate venture. The people on board know they're probably condemning their descendants to centuries of hardship with no guarantee of success. But it's the only option left, and maybe, just maybe, they make it. Maybe in 400 years, their descendants arrive at a new world and survive. Humanity gets a second chance, born from the ashes of the first. That's a dark scenario, but it's not implausible. In fact, some researchers think that crisis-driven missions are more likely than exploratory ones. Humans are notoriously bad at planning for the long term when there's no immediate threat. We tend to react to crises rather than prevent them. A generation ship might only happen when we have no other choice, but let's return to a more optimistic scenario. Let's say we do build a generation ship in a thoughtful, well-planned way. We've established colonies throughout the solar system. We've developed the technology. We've solved the genetic, social, and engineering challenges as best we can. We select a crew of a few thousand people who volunteer, fully informed of what they're signing up for. The ship launches and the mission begins. What is life like on that ship? What do people do all day? In science fiction, generation ships are often depicted with various environments: parks, lakes, forests, cities. The reality would probably be more utilitarian. Space and resources are at a premium. You'd have living quarters, probably smaller than a typical apartment. You'd have workspaces, farms, workshops, control rooms, laboratories. You'd have communal areas, dining halls, meeting rooms, maybe some recreational facilities like a gym or a garden. Work would be central to life. Everyone would have jobs essential to the ship's functioning, maintaining life support, growing food, repairing systems, teaching children, caring for the sick, managing resources. It would be a society where everyone contributes, because there's no room for freeloaders. If you don't work, people die. That level of interdependence could create a strong sense of community, but it could also create resentment and pressure. Education would be critical. Each generation needs to learn the skills necessary to run the ship. You need engineers who understand the propulsion system, biologists who manage the ecosystem, doctors who can treat injuries and illness, teachers who can pass on knowledge. But you also need artists, musicians, storytellers, people who maintain the culture and provide meaning and beauty in an otherwise stark existence. What do people do for fun? Entertainment would be mostly digital: books, movies, music, games, virtual reality. Physical recreation would be limited by space. Maybe there's a small park, a pool, a sports court. Social interaction would be a major form of entertainment. With only a few thousand people, you'd know everyone, or at least know of everyone. Gossip, friendships, romances, rivalries would all be amplified by proximity. And what about religion and philosophy? How do people find meaning in a multi-generational journey through the void? Some might maintain earth religions, passing down Christianity, Islam, Hinduism, Buddhism, or other faiths across generations. But those religions might evolve in isolation, developing new interpretations and practices. You might see the emergence of new religions or philosophies specific to the ship, perhaps centered around the journey itself, the destination, or the idea of humanity's cosmic purpose. There would inevitably be a tension between the mission and individual desires. The ship has a purpose: reach the destination, establish a colony. But the individuals living on the ship have their own purposes: find happiness, pursue their interests, live meaningful lives. For the first generation, the ones who chose to go, those two purposes might align. They're pioneers, and the journey is their life's work. But what about the fifth generation or the 10th? They didn't choose this. They were born into it. The mission might feel like an obligation imposed on them by ancestors they never met. You might see rebellions, not necessarily violent ones, but cultural rebellions. A generation that rejects the mission's importance, that questions why they should sacrifice for a goal they'll never see achieved. Or perhaps the opposite, a generation that becomes so focused on the mission that they lose sight of living, turning the ship into a joyless, purely functional environment where everything is subordinated to efficiency and survival. Maintaining balance between these extremes would be one of the great challenges of generation ship governance. How do you keep people motivated across centuries? How do you ensure each generation understands and accepts the mission without feeling enslaved by it? How do you allow for individual freedom and fulfillment while maintaining the discipline and cooperation necessary for survival? One approach might be storytelling and myth-making. Create a powerful narrative around the mission, a story that gives people a sense of identity and purpose. We are the voyagers. We carry humanity to the stars. Our ancestors chose this path, and we honor them by continuing it. Our descendants will walk on a new world because of what we do today. Turn the journey itself into something sacred, something worth preserving and passing on. But narratives can be double-edged. They can inspire, but they can also constrain. What if someone doesn't fit the narrative? What if they don't want to be a voyager, don't feel the call of the mission? In a small, closed society where the dominant narrative is so powerful, dissent could be dangerous. You might see conformity enforced not by law but by social pressure, ostracism of those who question or reject the mission. There's also the question of how information is preserved and transmitted across generations. Digital storage is efficient but vulnerable. Hard drives degrade, data can be corrupted, formats can become obsolete. A generation ship needs to preserve not just the technical knowledge required to operate the ship, but also human culture, history, science, art, literature. You're carrying the entirety of human civilization in a data archive. Some researchers propose using multiple redundant formats: digital storage, physical books printed on durable materials, even engraved metal plates as a last resort. You might establish a library as one of the ship's most important institutions, a repository of human knowledge maintained by specialized librarians who ensure information is preserved, backed up, and accessible. But who decides what information to include? You can't bring everything. Storage space, even digital storage, isn't infinite. Do you prioritize scientific and technical knowledge over art and literature? Do you include controversial or objectionable materials? Or do you curate the archive to exclude things the mission planners find undesirable? That's censorship, but it's also practical. If you're trying to build a cohesive society, do you really want to include materials that might promote division or extremism? And what about history? Do you tell the full, unvarnished truth about human history on Earth, including wars, genocides, slavery, oppression? Or do you present a sanitized version that emphasizes humanity's achievements and downplays its atrocities? The former is more honest, but it might foster cynicism or despair. The latter is more inspiring, but it's a lie, and lies have a way of unraveling. Let's talk about something practical: medical care on a generation ship. You need doctors, nurses, medical equipment, and pharmaceuticals. But some medical supplies have limited shelf lives. Vaccines, antibiotics, even basic medicines degrade over time. You can't pack 400 years' worth of penicillin, so you need pharmaceutical manufacturing capabilities on the ship. You need to be able to synthesize drugs from raw materials. That requires equipment, expertise, and feedstock chemicals. You also need genetic diversity in your medical knowledge. Different populations respond differently to medications. If your crew is diverse, your medical protocols need to account for that. Surgery is another challenge. You need surgical instruments, anesthesia, sterile environments. On Earth, if a surgery goes wrong, you can transfer the patient to a better equipped hospital. On a generation ship, you have what you have. There's no backup, no calling for a specialist from another city. Your doctors need to be capable of handling everything from routine procedures to complex emergency surgeries with limited resources. And what about mental health? Living in a confined environment for your entire life, knowing you'll never see Earth or the destination, could take a psychological toll. Depression, anxiety, and other mental health issues would likely be common. You'd need psychologists, psychiatrists, and probably a culture that normalizes mental health care and reduces stigma. But psychiatric medications also have shelf lives, and synthesizing them might be even more complex than synthesizing antibiotics. You'd need pharmaceutical chemists with a very broad skill set, and if mental health issues become widespread, as they well might, you could face a crisis where the demand for treatment exceeds your capacity to provide it. Then there's the question of what happens if someone commits a serious crime. Murder, assault, rape. These are tragic possibilities in any human society, and a generation ship is no exception. In fact, the close quarters and stress might increase the risk. On Earth, we have prisons, courts, extensive legal systems. On a generation ship, space is too valuable to dedicate to prisons, and you can't afford to take productive members out of the workforce indefinitely. So, what do you do with a murderer? Execution is one option, but many cultures have moved away from capital punishment on ethical grounds, and you're also reducing your already small population, which could impact genetic diversity. Rehabilitation is another option, but what if the person is deemed too dangerous? Exile is impossible in space. You can't banish someone from the ship. There's nowhere for them to go. Some proposals suggest cryogenic imprisonment, freezing the offender for a period of time as punishment. They're taken out of society. They experience time loss as a penalty, but they're not dead and they're not consuming resources. When they're thawed, they undergo rehabilitation and are reintegrated. But that requires cryogenic technology that, as we've discussed, we don't currently have. Or perhaps you take a restorative justice approach, focusing on repairing harm and reintegrating offenders rather than punishing them. That might work for lesser crimes, but for serious violent crimes, the victim's family and the community might demand something more. Justice is complicated enough on Earth, with centuries of legal philosophy and practice to draw on. On a generation ship, you're building legal systems from scratch, and you have to get it right because there's no higher court to appeal to. Let's consider another scenario. What if the ship encounters something unexpected? Space is vast and mostly empty, but it's not entirely empty. There are rogue planets drifting between stars, orphaned from their parent systems. There are clouds of gas and dust. There are cosmic ray sources and potentially uncharted gravitational anomalies. What if, 200 years into the journey, the ship detects a rogue planet in its path? It's not a direct collision course, but it's close enough that the planet's gravity will perturb the ship's trajectory if they don't adjust. They can avoid it by altering course, but that requires fuel, and any course change means recalculating the trajectory to the destination. A small change early in the journey might mean missing the target star system entirely, or arriving centuries later than planned. The crew has to make a decision: risk passing close to the planet and hoping the gravitational effect is manageable, or spend precious fuel to adjust course. Neither option is great, and this is a decision being made by people who weren't part of the original mission planning, who are living with the consequences of choices made by their great-great-grandparents. Or suppose the ship detects a signal, not a natural radio source, but something artificial, something that suggests intelligence. It's coming from a star system 30 light-years away, off the ship's course. Do they investigate? Do they try to respond? Do they alter course to make contact, even though that means abandoning the original mission and traveling to an unknown destination? The original mission planners probably didn't anticipate this scenario. There's no protocol for it. The crew has to decide based on incomplete information and the values of their society, which may have drifted from Earth values over generations. Some might argue that making contact with alien intelligence is worth any risk, that it's the most important discovery in human history. Others might argue that the mission is to reach the designated planet, and nothing should distract from that goal. The debate could tear the community apart. And what if the signal isn't friendly? What if it's a warning, or worse, something hostile? A generation ship is not a warship. It has no weapons, no defenses beyond perhaps some shields against micrometeors and radiation. If there's hostile intelligence out there, the ship is utterly vulnerable. Even if the aliens aren't hostile, contact could be dangerous. There's the biological risk of alien diseases, the technological risk of being outmatched, the cultural risk of contact disrupting the ship's social order. These are scenarios that sound like science fiction, and maybe they are. Space is so vast that the odds of encountering anything during the journey are vanishingly small. But vanishingly small isn't zero, and over a 400-year journey through interstellar space, even unlikely events become possible. There would inevitably be a tension between the mission and individual desires. The ship has a purpose: reach the destination, establish a colony. But the individuals living on the ship have their own purposes: find happiness, pursue their interests, live meaningful lives. For the first generation, the ones who chose to go, those two purposes might align. They're pioneers, and the journey is their life's work. But what about the 5th generation or the 10th? They didn't choose this. They were born into it. The mission might feel like an obligation imposed on them by ancestors they never met. You might see rebellions, not necessarily violent ones, but cultural rebellions. A generation that rejects the mission's importance, that questions why they should sacrifice for a goal they'll never see achieved. Or perhaps the opposite. A generation that becomes so focused on the mission that they lose sight of living. turning the ship into a joyless, purely functional environment where everything is subordinated to efficiency and survival. Maintaining balance between these extremes would be one of the great challenges of generation ship governance. How do you keep people motivated across centuries? How do you ensure each generation understands and accepts the mission without feeling enslaved by it? How do you allow for individual freedom and fulfillment while maintaining the discipline and cooperation necessary for survival? One approach might be storytelling and myth-making. Create a powerful narrative around the mission, a story that gives people a sense of identity and purpose. We are the voyagers. We carry humanity to the stars. Our ancestors chose this path, and we honor them by continuing it. Our descendants will walk on a new world because of what we do today. Turn the journey itself into something sacred, something worth preserving and passing on. But narratives can be double-edged. They can inspire, but they can also constrain. What if someone doesn't fit the narrative? What if they don't want to be a voyager, don't feel the call of the mission? In a small, closed society where the dominant narrative is so powerful, dissent could be dangerous. You might see conformity enforced not by law but by social pressure, ostracism of those who question or reject the mission. There's also the question of how information is preserved and transmitted across generations. Digital storage is efficient but vulnerable. Hard drives degrade, data can be corrupted, formats can become obsolete. A generation ship needs to preserve not just the technical knowledge required to operate the ship, but also human culture, history, science, art, literature. You're carrying the entirety of human civilization in a data archive. Some researchers propose using multiple redundant formats: digital storage, physical books printed on durable materials, even engraved metal plates as a last resort. You might establish a library as one of the ship's most important institutions, a repository of human knowledge maintained by specialized librarians who ensure information is preserved, backed up, and accessible. But who decides what information to include? You can't bring everything. Storage space, even digital storage, isn't infinite. Do you prioritize scientific and technical knowledge over art and literature? Do you include controversial or objectionable materials? Or do you curate the archive to exclude things the mission planners find undesirable? That's censorship, but it's also practical. If you're trying to build a cohesive society, do you really want to include materials that might promote division or extremism? And what about history? Do you tell the full, unvarnished truth about human history on Earth, including wars, genocides, slavery, oppression? Or do you present a sanitized version that emphasizes humanity's achievements and downplays its atrocities? The former is more honest, but it might foster cynicism or despair. The latter is more inspiring, but it's a lie, and lies have a way of unraveling. If you are still watching, make sure to subscribe to the channel. You'll be joining a community of curious minds who aren't afraid to confront the hard truths about our place in the cosmos. Now let's talk about something practical: medical care on a generation ship. You need doctors, nurses, medical equipment, and pharmaceuticals, but some medical supplies have limited shelf lives. Vaccines, antibiotics, even basic medicines degrade over time. You can't pack 400 years worth of penicillin. So you need pharmaceutical manufacturing capabilities on the ship. You need to be able to synthesize drugs from raw materials. That requires equipment, expertise, and feedstock chemicals. You also need genetic diversity in your medical knowledge. Different populations respond differently to medications. If your crew is diverse, your medical protocols need to account for that. Surgery is another challenge. You need surgical instruments, anesthesia, sterile environments. On Earth, if a surgery goes wrong, you can transfer the patient to a better equipped hospital. On a generation ship, you have what you have. There's no backup, no calling for a specialist from another city. Your doctors need to be capable of handling everything from routine procedures to complex emergency surgeries with limited resources. And what about mental health? Living in a confined environment for your entire life, knowing you'll never see Earth or the destination, could take a psychological toll. Depression, anxiety, and other mental health issues would likely be common. You'd need psychologists, psychiatrists, and probably a culture that normalizes mental health care and reduces stigma. But psychiatric medications also have shelf lives, and synthesizing them might be even more complex than synthesizing antibiotics. You'd need pharmaceutical chemists with a very broad skill set. And if mental health issues become widespread, as they well might, you could face a crisis where the demand for treatment exceeds your capacity to provide it. Then there's the question of what happens if someone commits a serious crime. Murder, assault, rape, these are tragic possibilities in any human society, and a generation ship is no exception. In fact, the close quarters and stress might increase the risk. On Earth, we have prisons, courts, extensive legal systems. On a generation ship, space is too valuable to dedicate to prisons, and you can't afford to take productive members out of the workforce indefinitely. So what do you do with a murderer? Execution is one option, but many cultures have moved away from capital punishment on ethical grounds, and you're also reducing your already small population, which could impact genetic diversity. Rehabilitation is another option, but what if the person is deemed too dangerous? Exile is impossible in space. You can't banish someone from the ship. There's nowhere for them to go. Some proposals will suggest cryogenic imprisonment, freezing the offender for a period of time as punishment. They're taken out of society. They experience time loss as a penalty, but they're not dead and they're not consuming resources. When they're thawed, they undergo rehabilitation and are reintegrated, but that requires cryogenic technology that, as we've discussed, we don't currently have. Or perhaps you take a restorative justice approach, focusing on repairing harm and reintegrating offenders rather than punishing them. That might work for lesser crimes, but for serious violent crimes, the victim's family and the community might demand something more. Justice is complicated enough on Earth, with centuries of legal philosophy and practice to draw on. On a generation ship, you're building legal systems from scratch, and you have to get it right because there's no higher court to appeal to. Let's consider another scenario. What if the ship encounters something unexpected? Space is vast and mostly empty, but it's not entirely empty. There are rogue planets drifting between stars, orphaned from their parent systems. There are clouds of gas and dust. There are cosmic ray sources and potentially uncharted gravitational anomalies. What if, 200 years into the journey, the ship detects a rogue planet in its path? It's not a direct collision course, but it's close enough that the planet's gravity will perturb the ship's trajectory if they don't adjust. They can avoid it by altering course, but that requires fuel, and any course change means recalculating the trajectory to the destination. A small change early in the journey might mean missing the target star system entirely, or arriving centuries later than planned. The crew has to make a decision: risk passing close to the planet and hoping the gravitational effect is manageable, or spend precious fuel to adjust course. Neither option is great, and this is a decision being made by people who weren't part of the original mission planning, who are living with the consequences of choices made by their great-great-grandparents. Or suppose the ship detects a signal, not a natural radio source, but something artificial, something that suggests intelligence. It's coming from star system 30 light-years away, off the ship's course. Do they investigate? Do they try to respond? Do they alter course to make contact, even though that means abandoning the original mission and traveling to an unknown destination? The original mission planners probably didn't anticipate this scenario. There's no protocol for it. The crew has to decide based on incomplete information and the values of their society, which may have drifted from Earth values over generations. Some might argue that making contact with alien intelligence is worth any risk, that it's the most important discovery in human history. Others might argue that the mission is to reach the designated planet, and nothing should distract from that goal. The debate could tear the community apart. And what if the signal isn't friendly? What if it's a warning, or worse, something hostile? A generation ship is not a warship. It has no weapons, no defenses beyond perhaps some shields against micrometeors and radiation. If there's hostile intelligence out there, the ship is utterly vulnerable. Even if the aliens aren't hostile, contact could be dangerous. There's the biological risk of alien diseases, the technological risk of being outmatched, the cultural risk of contact disrupting the ship's social order. These are scenarios that sound like science fiction, and maybe they are. Space is so vast that the odds of encountering anything during the journey are vanishingly small. But vanishingly small isn't zero, and over a 400-year journey through interstellar space, even unlikely events become possible. So where does all of this leave us? We've explored the engineering challenges, the biological constraints, the social dynamics, the ethical dilemmas, the psychological factors, and the astronomical uncertainties. We've imagined what life might be like on a generation ship and what might happen when it arrives. We've considered optimistic scenarios and dystopian ones, practical solutions and philosophical quandaries. The fundamental question remains: should we build generation ships? There's no simple answer. It depends on what we value, what we believe about humanity's purpose and future, and what we're willing to sacrifice to achieve it. If you believe that humanity's long-term survival and expansion are paramount, that we have a destiny among the stars, then generation ships might be worth pursuing despite all the challenges and risks. The investment would be enormous, the timeline spans centuries, and success is far from guaranteed, but the potential payoff, ensuring humanity survives even if Earth doesn't, spreading consciousness and intelligence throughout the galaxy, might justify it all. If you believe that our responsibilities are primarily to people living now, that we should focus on solving Earth's problems before we dream of other worlds, then generation ships might seem like a dangerous distraction. The resources required could address poverty, disease, climate change, and countless other urgent issues. Why invest in a project that won't benefit anyone alive today when there's so much suffering that could be alleviated right now? There's also a middle position, that we should develop the technologies and capabilities necessary for generation ships, closed-loop life support, advanced propulsion, long-term preservation of information and genetic material, because those technologies have applications here on Earth. Learning to build sustainable, self-sufficient habitats in space might teach us how to build more sustainable communities on Earth. The engineering and scientific advances required for interstellar travel might yield unexpected benefits in medicine, energy, materials science, and other fields. In this view, the journey toward generation ships is as valuable as the destination. Even if we never actually build one, the attempt pushes us to innovate, to think long-term, to work together on challenges that transcend national borders and immediate concerns. It gives us a goal that's genuinely ambitious, that requires the best of human creativity and determination. Personally, I think generation ships are unlikely to be built in the near future, the next century or two, but they might become feasible and desirable further down the line. Here's how I imagine it might unfold. Humanity establishes a permanent presence in space. We build bases on the Moon and Mars, develop mining and manufacturing in the asteroid belt, create rotating habitats at Lagrange points. We develop better propulsion systems, advanced life support, and experience maintaining closed ecosystems. We send robotic probes to nearby star systems, gathering detailed data about exoplanets. This phase is about building infrastructure and gaining experience. With established space infrastructure, we begin considering interstellar missions more seriously. Maybe we send the first generation ship as a test case, not to a distant star but to the outer solar system or a nearby star like Proxima Centauri. This is a proof of concept, a way to test the technology and social systems on a smaller scale. Maybe it's not even meant to be permanent. Maybe it's designed to return, or at least to maintain close contact with the solar system. If the test missions succeed, we begin launching generation ships to more distant destinations. By this time, we might have technologies we can barely imagine now. Better propulsion, possibly even breakthrough physics that makes faster-than-light travel feasible, though that's purely speculative. Or maybe we stick with generation ships, but make them better, more comfortable, more capable of supporting large populations indefinitely. This gradual approach allows us to develop the necessary technology and social structures without betting everything on a single enormous project. It lets each generation make its own choices about how far and fast to pursue interstellar colonization, rather than committing distant descendants to a path they might not want. But there's another possibility that could change everything: life extension and suspended animation. If we develop the ability to extend human lifespans significantly, or to safely freeze people for decades or centuries, then generation ships might become unnecessary. Instead of a multi-generational journey, you could have a single-generation journey where the crew is either frozen for most of the trip or lives long enough to see the destination themselves. This solves many of the ethical problems we've discussed. People who choose to go actually get to complete the journey. They're not condemning their children and grandchildren to a life in space. The social dynamics are simpler because you're not dealing with cultural drift across generations. And if the destination turns out to be unsuitable, the crew might be able to return to Earth within their extended lifespans. Of course, this introduces its own challenges. Developing reliable cryonics or life extension is far from trivial, but it's a possibility worth considering. Medical science is advancing rapidly, and what seems impossible now might be routine in a century or two. There's also the question of whether biological humans are the right choice for interstellar exploration at all. Maybe we'll develop artificial intelligence that's conscious and capable of independent action. Maybe we'll enhance humans with cybernetic implants or genetic modifications that make space travel easier. Maybe we'll upload human consciousness into digital form, allowing us to travel as information transmitted at light speed, rather than as physical bodies crawling through space at a fraction of that speed. These transhumanist scenarios might sound like science fiction, but they're taken seriously by researchers in AI, neuroscience, and related fields. If consciousness can exist in substrates other than biological brains, then interstellar exploration becomes vastly easier. Digital minds don't need air, food, or gravity. They don't age or get bored. They can be backed up, preventing loss from accidents. They could make the journey in simulated environments where subjective time passes differently, so a 400-year journey feels like much less. But this raises profound philosophical questions. Would a digital copy of you actually be you, or just a copy that thinks it's you? If we send AI or uploaded minds to the stars instead of biological humans, is that still human expansion, or have we created something fundamentally different? Would we be comfortable with the idea that humanity's future might not involve biological humans at all? These are questions for philosophers, ethicists, and society as a whole to grapple with. There are no easy answers, and different people will reach different conclusions based on their values and beliefs about consciousness, identity, and what it means to be human. Let me bring this to a close with some final thoughts. Generation ships represent one of the most ambitious ideas in human history, the deliberate expansion of our species to other star systems through journeys that span centuries. They're technically possible, at least in principle, though fraught with engineering, biological, and social challenges that we're only beginning to understand. Whether we should pursue them is a question that mixes science with philosophy, practical concerns with visionary dreams. It asks us to think beyond our own lifetimes, to consider what we owe to future generations and what responsibilities we have to preserve and expand humanity's presence in the universe. My own view is that the conversation itself is valuable. Thinking about generation ships forces us to confront big questions. What is humanity's purpose? How do we balance present needs with future possibilities? What risks are acceptable in pursuit of exploration and survival? How do we govern ourselves in extreme circumstances? What does it mean to be human when separated from Earth for generations? These questions have relevance beyond space travel. They touch on how we address climate change, how we structure our societies, how we preserve knowledge and culture, how we make decisions that affect people not yet born. Engaging with generation ships as a thought experiment, even if we never build one, makes us think more clearly about these fundamental issues. And who knows, maybe centuries from now, our descendants will look back at this era as the beginning of humanity's expansion to the stars. Maybe there will be human civilizations on dozens or hundreds of worlds, each with its own culture and history, all tracing their origins back to Earth. And maybe some of them will have arrived there on generation ships, vessels that carried humanity across the void through the determination and sacrifice of countless generations who believed the journey was worth it. Or maybe we'll find other ways to reach the stars. Maybe we'll stay on Earth and be content with our one planet, focusing on making it the best home it can be. Maybe we'll go extinct before we get the chance. The future is uncertain, and we can't know what path humanity will take, but we can imagine, we can plan, we can explore the possibilities, weigh the options, and make informed choices about what kind of future we want to pursue. That's what conversations like this are for, to think deeply, to question assumptions, to envision what might be possible, and to decide what's worth striving for. Generation ships are, in the end, about hope. Hope that humanity has a future beyond Earth. Hope that we can overcome incredible challenges. Hope that the journey itself is meaningful even if we never see the destination. Whether that hope is justified, whether the risks and sacrifices are worthwhile, whether we have the wisdom and determination to make it work. Those are questions each generation will have to answer for themselves. But here's the thing, we just scratched the surface. The real nightmare? The journey itself to Proxima Centauri. I break down every horrifying detail in this video right here. The terrifying reality of a journey to Proxima Centauri. Trust me, you need to see this.